All right, everyone, welcome to next video. I'm talking about types of work, and here we're going to talk about reversible expansion work. So first, we're going to define what is reversible. Okay. Excuse me. So reversibility of some process is a process in which you make small changes away from equilibrium such that you're essentially always maintaining equilibrium while you're making these changes. Okay. Right, and it's called reversible, this type of work and this type of change is called reversible because in the case of doing something reversibly, you can bring your system back to where it started and the surroundings. Okay, so irreversible changes, okay, like a constant pressure expansion, you can bring your system back to where it started, but when you do so, there will be some net change in the surroundings. Okay, but if you do an expansion and a compression reversibly, you're able to bring the system and the surroundings back to where they started, so there's no net change in the universe. But if you do some process irreversibly, there's a net change in the universe, and that cannot be undone, right? So reversible expansion is expansion that's always at equilibrium, okay? Now, if we recall, right, equilibrium, when we're talking about kind of gases and pressures, right, is related with mechanical, right, equilibrium, right? And that mechanical equilibrium means that the internal pressure, right, and the external pressure are always equal, okay? So during a reversible expansion of a gas, the pressure inside your container and outside your container, right, your system and surroundings pressure are always equal, okay? So then how do we solve that, right? So let's talk about the reversible isothermal expansion of a gas, okay? Assuming we have an ideal gas here, right? Now, because it's reversible, that means P external equals the pressure of my gas. So now this integral is now the integral of the pressure of my gas times some change in volume. Well, the pressure of my gas depends on the volume based off of the ideal gas law. So I plug that in, solve the integral, and we get this equation here, okay? And so this equation gives us how much work is being done when I reversibly isothermally expand my gas, right, from some initial volume to some final volume. Okay. So if we kind of look at that pictorially, again, the amount of work that's being done is this area under the curve, but now I'm going from some initial pressure and volume to some final pressure and volume, right, where my pressure externally changes with the change in my internal pressure, okay? And so now the work that's being done is the area under this curve, okay, here, right? Now, keep in mind that this expression here is only true for an ideal gas, and for a real gas where we use the van der Waals equation state or Vero equation state, there would be a different expression for work, right? So just kind of comparing this reversible isothermal work versus the constant pressure work, right? We see that for this constant pressure work versus reversible isothermal, right? The constant pressure work gives us this area under the curve, and then for a reversible change, we get this area plus this original area, okay? So we note here that for a reversible process, you will always get more work out than if you do something irreversible. Okay? If you reversibly expand or compress your gas, you will do more work than if you do that expansion or compression irreversibly. Okay? Right? And that's always going to be true, that the reversible heat transfer, just like the reversible amount of work, is always greater than the irreversible value. Okay? And so that's it for the type of work that we can do, right? We can either expand against no external pressure, right? In which case the work is zero. We can expand against a constant external pressure, right? In which case the work is equal to minus P external delta V. Or we can expand isothermally and reversibly, in which case the work is equal to minus nRT ln of V final over V initial.